Welcome back, chemistry students. Today we're going to learn about strengths of acids and bases, because not all acids have the same strength, not all bases do as well. And you guys know that chemists like to put numbers on things, and there is a way to put a number on an acid and a base to distinguish which acids are a little bit stronger than others. We're actually going to learn about another constant today. I know how you guys like those constants. Like we have the KEQ, the KSP. We've learned about all those different constants. Well, there's going to be two more constants that we're going to learn about today. One's going to be the Ka, which is the acid dissociation constant. And the other one we're going to learn about is the Kb, which is the base dissociation constant. It just basically tells us how strong the acid or the base is. So let's just kind of get this thing started. So what do you mean? So you might be wondering, what do you mean that some acids are stronger than others, and then how is that defined? Okay, so strong acids are going to completely ionize in an aqueous solution. So if we have hydrochloric acid, just pure HCl, okay, and you put it in an aqueous solution with water, it is 100% gonna ionize, and we're gonna get H plus ions, and we're gonna get the Cl minus ions. This is a strong acid. It 100% completely dissociates, completely ionizes in water. Weak acids, on the other hand, and you guys should know what this symbol means, right? It's a reversible reaction, versus this one goes to completion. It only partially ionizes, or it slightly ionizes. So if you have ethanoic acid, which is known to be a weak acid, it's going to dissociate water and give us a little bit of the H plus and a little bit of this, but we're still going to have a lot of the water and a lot of the compound here in the solution. So weak acids only slightly ionize, where strong acids are going to completely ionize. So now it's kind of like, all right, so strong acids are in their own category. They completely ionize, they're strong. Now weak acids, how do we tell, which one's stronger than the other? And you guys might be doing some brainstorming, thinking back in chapter 18, going, well, the K equilibrium told us something, and this is a reversible reaction, so couldn't we technically do like a products over reactants thing here to come up with another constant? The answer is yes. That's actually what chemists do. It actually works out good for us, because if you have a lot of this, that means the acid's stronger, right? So if you have a lot of product, that means the acid's going to be strong. If you have a lot of the reactant, that means the acid's going to be weak. And so let's get to it. To give you an idea of a visual of what I'm trying to say here is a strong acid completely dissociates. You start with the HA. Now the diagram uses HA mainly because it's just the general form, because you guys know that acids have a hydrogen in them. So the general form HA, right? So complete dissociates, you're going to get the hydronium, which is H plus, and the anion, that's what A is standing for. For weak acids, when it dissociates, you're going to have a little bit of the acid still ionized, and then you're going to have a little bit of the H plus and the anion. For weaker acids, you're going to have very little amounts of it being ionized, and you'll still have a lot of the original acid in its form. But yeah, there's a way to calculate the difference, and that's what we're going to do today. Is we're going to use the Ka. We're going to be able to tell, categorize these weaker acids. So I've been hinting at it, I've been saying it. So like it says here, how does the Ka of an acid dissociation constant relate to the strength of the acid? Okay, well, to help us answer that question, let's look at the formula here. Okay, so let's just say we have, I'll write the equation for where they're coming up with this. Let's just say you have ethanoic acid, which is CH3, and then COOH, you place that in water, it's going to reach an equilibrium because you're going to have a little bit of everything, and you're going to get the H plus ion, plus you're going to get the anion that's produced when it ionizes. All right, so that's the equation we're looking at. If you write the KEQ for it, I think you guys can see, here's the products, here's the reactants, so we can write a KEQ for this, which is great, but really, we don't really need to know how much water is there, because we're just concerned with the acid. We really just want to know, okay, what is the acid concentration compared to its ions? So what chemists have done is they just kind of multiply it times this KEQ, or just kind of forget about it, and then they call it the Ka. Because that's really all we're interested in. We're just interested in looking at the ion concentrations compared to the original acid. So that's what the Ka is derived from. So obviously, so now we have the formula right here. The more of these you have, isn't that going to make the number greater, right? You guys should know that from chapter 18. So the higher these are, the higher, or the stronger the acid's going to be. So then obviously the smaller these numbers are, the weaker the acid is going to be. So it's a very useful way of helping us distinguish between strong acids and the weaker acids. So this actually puts it into words for you here. Weak acids have a small Ka value. They have a small Ka value because they only partially ionize to give us H plus and the anion. These numbers are going to be small, right? Think back to the diagram. If we have a weak acid, we're going to have very small amounts of these guys right here. And we can actually calculate it. So the smaller the Ka, the weaker the acid. Yes, you have to know on that test. You have to know that on your homework assignments. And vice versa. The stronger an acid is, the larger the Ka is going to be. So it's simple math. We've been doing this since chapter 18. So it's just another constant. Just a useful thing for us. So if we look at this table, we should be able to pick out, so here's some Ka values right here. We should be able to pick out the strongest and the weakest acids from this table. Let's see here, if I'm doing a general scan, double digit. So I got this one right here. That's going to be our weakest acid. And then looking in here, this would be our, it's like the strongest of the weak, because technically this isn't the strongest acid out there, but it's the strongest in our table. So yeah, so that's the Ka. So the smaller the Ka, the weaker the acid. The higher the Ka, the stronger the acid. The base dissociation constant is derived the same way. It's just going to be that same ratio, but instead of it being the H plus and the A minus, it'll just include that hydroxide ion. Strong bases and weak bases are going to do the same thing. Your strong bases are going to dissociate completely into the metal ions and the hydroxide ions. The weak bases will just partially ionize. So to kind of give you guys a summary, if you're looking at this table right here, the strong bases and the weak bases do the same thing here. You would just replace the A with the hydroxide ion, and then I'll just do a big M for the metal, because you guys know a lot of bases have a metal attached to a hydroxide. So when it dissociates, you're going to get metal and hydroxide. When it's a strong base, down here you see, so it's the same diagram, just a base. All right. Which therefore we can use the same type of constant, the Kb. So what we can do is do the same thing. Just take the ratio of those the hydroxide ions and the metal and divide it by the total. So here's kind of an example of it. So there it is right here. There's the ions compared to the original form. it's basically the same thing. Again, we don't care about water. That's not going to be useful to us, so they just get rid of it and they call it the KB. So for the KB, it's just that over this. Think of it a lot of is like products over reactants, but we're just ignoring the water because we don't care about the water. All right, so this table will be very helpful for you. In my chemistry class, I had to memorize the strong acids and the strong bases. This is a very good table for you guys to look at because there will be some multiple choice questions. What would be considered a strong acid? What would be considered a strong base? So here's kind of your typical strong acids: hydrochloric acid, nitric acid, sulfuric acid. These ones are going to be your strong acids. Down here, these will be your strong bases. Your potassium hydroxides, your sodium hydroxide, your calcium hydroxide. So yeah, and these ones are kind of your weaker acids, your hypochlorous acid, your carbonic acid, your ethanoic acid. Those ones are your weaker ones. We use Ka values for these. We use Kb values for some of these. So, but yeah, I had to memorize the acids and bases in my college chem class. Just something, it's a really good thing to know. You might be wondering, well, how do you tell? Well, the easiest way to kind of tell, I mean, it's not a foolproof system because there's always an exception to the rule, but you know, a lot of times if it's just H and another thing attached to it, so like here, HCl, that's going to be a strong acid. If it's H3PO4, that's kind of a weaker acid. You got a lot of hydrogens here and a lot of this. It takes a lot to dissociate that. So here's kind of the exception to the rule. It says H attached to the polyatomic ion chlorate. However, it's almost like into that neutral range. Okay, so let's calculate these dissociation constants. How can